First question wants to know how many pi electrons there are in that molecule. So let's just remind you about what is going on in a double bond and what's going on in a benzene ring. So in a double bond, remember, this is the important picture, and you actually need to be able to draw this. So if you can't, this would be a good chance to remind yourself about that. So if we just focus on the sigma bonds, which remember is where you have p orbitals overlapping end over end, or s orbitals overlapping, you have that framework around the double bond. And to make the second component of the double bond, you have this. So you have a p orbital here and a p orbital there, each containing one electron. And the point is that you get sideways overlap. Okay, so this is the diagram you would draw: sideways overlapping p orbitals. And what that generates is your localized pi bond, which you draw like this. And of course, because each of these carbons contributed one electron, then the bond has a pair of pi electrons. So that's a localized. Localized just means that the electrons are constrained to just occupying this space between the two atoms. They can't stray any further than that. So that's a localized pi bond. And like any bond, or any localized bond, it's a shared pair of electrons, so that has two electrons. Okay, so you're going to get two electrons from the pi bond there, and also two electrons from the pi bond here. Remember, a double bond in a carbonyl group is the same kind of arrangement. It's just a sigma bond and a pi bond, this time between carbon and oxygen. So that's going to give you two electrons, so is this. In a benzene ring, again, you need to be able to draw the picture. So remember, this time, if that's your sigma bonded framework, with the 6 carbons all bonded to each other, what you need to be able to draw this time is this kind of picture. Okay, and again, you can see that you've got sideways overlapping p orbitals, again with one electron per orbital, because each carbon is making 3 sigma bonds, so it's only got one electron left over to contribute to the pi electron system. So that leads to your delocalized system, which you draw like this. There's your hexagon of sigma bonds, then you just draw a ring above like that, and a ring below like that, and that's your delocalized pi system. So 1 electron from each atom means 6 electrons altogether in the delocalized system. So the total number of pi electrons in that molecule is 6 from this, 2 from this, 2 from this, which is 10 altogether. So in the second part, it's focusing on the synthesis of this compound, starting from that one. Now in the test, it made this relatively straightforward by basically telling you what the stages of the synthesis were, and just asking you to fill in the details of the reagents. But just bear in mind that in a real exam, you would be quite likely in the position where you'd have to make up your own route with all the details. They would just say, right, this is what you've got to start with, that's where you've got to end up, and you have to be able to supply the reactions. So the key, if you had that situation, would be to look at this and realize that you're forming this new, you're forming a new carbon-to-carbon bond there. Okay, you've got a bond between the carbonyl and an oxygen here, but that's been replaced by a new carbon-to-carbon bond. And you don't know many reactions. In fact, at the moment, you really only know 2 reactions which form new carbon-to-carbon bonds. One of which is adding cyanide to a carbonyl group, and that's not relevant here because cyanide is not going to help you to make that benzene ring. But the other is the Friedel-Crafts reaction. So the idea is that you would look at this and you think, right, if I'm going to form this new carbon-to-carbon bond here, I need a Friedel-Crafts reaction. And remember the trick with Friedel-Crafts is just that whatever group you want to have the benzene ring added onto, so if we just put the benzene ring here in a different colour, that's what we want to substitute in, and in the Friedel-Crafts reaction, where that ring ends up, you want a chlorine. Okay, because that's how Friedel-Crafts works, that wherever there is a chlorine in an organic compound, it lets you substitute in an aromatic ring in its place. So that's the second step. Is that you need an acyl chloride in this case, and wherever the chlorine, you know, that's the easy way to remember, is wherever the chlorine is in the starting compound, that's where the benzene ring ends up in the product. And Friedel-Crafts requires a halogen carrier catalyst, so aluminium chloride would be the standard one, although you got the marks if you've got any group 3 halide, so iron 3 bromide or, you know, any of those kind of things would have got you the marks, but aluminium chloride is the standard one for that. So that was the catalyst for the second part, but it also wanted to know, well, how would you make this in the first place? And again, that's just a standard reaction that you have to know how to make an acyl chloride from a carboxylic acid, and the answer is that you use that compound, which is called thionyl chloride, but you don't need to know the name, you need to know the formula. Okay, so SOCl2 is the reagent which reacts with carboxylic acids to make acyl chloride, and that you just have to know. Okay, so as soon as you see an acyl chloride, that needs to be one of the bits of information that should pop into your mind. If I need to make it, I know how to do it. So that was the first answer, that was the second one. And just ask yourself, as I say, could you have put that whole story together? Because in the test it made it easy by sort of telling you what the steps were, but you need to make sure that you can do that independently. So the more practice you do with organic reactions, the easier those kind of questions will become. The next thing it wants you to do is percentage yield. So this is an absolutely standard kind of organic chemistry calculation which you nearly always will get in an organic paper. And remember what the percentage yield means, which in this case it tells you is 78%. It means however many moles of this you start with, you only get 78% of that number of moles. Remember, it's relating moles. Doesn't directly relate masses. You have to turn the masses into moles, and this number relates to moles. Okay, so you start out by working out the moles of this compound on the left, which is mass over mR, which is 10.0. And then you have to obviously add the MRs up quite carefully. Again, it's just a question of doing lots of practice. It's possible, I mean, where people go wrong, it's most commonly because they get the number of hydrogens wrong. So possibly it's worthwhile you going through and writing all the hydrogens on, but in the end, it's, if you practice enough, you don't really need to, because you just look at that carbon and you think, you know, that's a carbon on its own, it's got 3 hydrogens. This carbon's already got 3 bonds, so it's only got 1. So you can go through and say, right, that's 3, plus 1 is 4, plus 1 is 5. This carbon again has got 3 bonds already, so just 1 hydrogen is 6. That one's only got 1 bond, so that's got 3 hydrogens, takes it to 9 hydrogens. This one hasn't got any because it's got 4 bonds already, so that one is 10. Okay, so if you go through, you've got 10 hydrogens, 2 oxygens adds up to 32, with the 10 hydrogens comes to 42, and then count the carbons, 1, 2, 3, 4, 5, 6. So 6 12s are 72 plus 42 gives you 114. So try to get good at getting MRs reliably, and be aware that it's a very common mistake. So, you know, unless you're really rushing, just double check it, make sure you got it right. Okay, so that's your first step, that you need to know how many moles of starting material you had, and that comes to 0.08772. Keeping lots of significant figures at this point, because I don't want to round till the end. And then, as we said, what that number means is that you get 78% of that number of moles of your product. So you just multiply by 78 over 100 to get the moles of that compound, which gives you 0.06842. So then finally, you've got to turn that back into a mass. So you multiply by mR. And obviously the mR is different, because you've got rid of the OH, which means you've lost 17 from the mR, but you've replaced it with a phenyl group, which means you've added 77. So if you take away 17 and add 77, you add 60, which gives you an mR of 174.0 for that compound. And if you multiply that out, you get 11.9 grams, which is the answer. Okay, so practice some percentage yield questions. Sometimes you have to do it the other way around, work backwards and figure out how much starting material you must have had, or sometimes you have to calculate what the percentage yield is. So you've got to do it every which way around, but the key is remembering it's based on moles, and then they're not terribly difficult. Next, it asks you about the reaction of this with bromine. And this is getting at the difference in reactivity between an aromatic ring and an alkene group. You've not learnt anything about ketones reacting with bromine, so we don't make anything up. If you haven't learnt it, it doesn't happen. But you know about this and you know about this. And they're absolutely obsessively interested in this difference in reactivity. So this is a really key question. So last year when we did alkenes, you learnt that bromine will react with alkenes. And that was one of the classic electrophilic additions. Remember how they always work is that whatever you react with, it adds across the alkene group like that. So one bromine will add to one end, one will add to the other end. So the pi bond breaks and you get one bromine bonding there and one bromine bonding here. And we learned that that reaction happens very easily. So the test of decolorizing aqueous bromine was how we learnt to identify alkenes last year. Then when we got onto aromatic rings, we talked about the fact that, to our initial surprise, that fails to happen. If you add aqueous bromine to benzene, nothing happens. And we ultimately rationalized that by saying, oh, that's because the delocalization gives you decreased pi electron density in the ring, which makes it less attractive with an electrophile. So ultimately we discovered that you need to have a catalyst, AlBr3 or FeBr3, and only when you have that halogen carrier there will the aromatic ring react as well. In this question it just said aqueous bromine, no mention of a catalyst, so no reaction of the ring, and the correct product was that one. Next it tells us it's going to ask about nitration, but what it focuses on initially is the fact that this carbonyl group is an electron withdrawing group. And it tells you that because you're not expected to know that. The one that you're expected to know, which is electron withdrawing, is NO2. So if that was in the compound, they could ask you about these effects without telling you it's electron withdrawing. But anything else like this one, again, it made it a bit easier by telling you it was an electron withdrawing group. And you have to, first of all, understand what that means. And what it means is that the density of pi electrons in the ring is decreased compared to benzene because electron density is being pulled this way. It's basically because that oxygen is very electronegative, so it's pulling electron density this way, and it decreases the pi electron density in the ring. Okay, so that was the first thing, that you get decreased pi electron density in the ring. If we had an electron donating group like OH or NH2, it would have done the opposite. It would have pushed electron density into the ring, so we'd have increased pi electron density. So the first answer was that the electron density is lower than it is in benzene. And then it says, well, okay, what's the consequence of that for the rate of an electrophilic substitution like nitration. And the key idea is, remember, that this is about attraction between the delocalized electron system, high electrons in the ring, and whatever your electrophile is. So in the case of nitration, remember it's NO2+. And basically, the stronger the attraction between the electrophile and the pi electrons of the ring, the more likely it is that a pair of electrons is going to jump out of the ring and be grabbed by the electrophile like that. So that's the key first step in electrophilic substitution. And how attractive that is just depends on the pi electron density. The more electron density, the more negative, so the stronger the attraction. That's what this is getting at. So what you explain is that decreased pi electron density in the ring makes it less attractive to an electrophile, like NO2+, but it just asks you in general here. So less attractive to an electrophile, and therefore less reactive than your reference compound, which is just benzene. Okay, so again, that story about the effects of electron withdrawing groups and electron donating groups, you've got to be confident about that. They could ask you about either one of them. But that's the story. You learn that for NO2 as a substituent, but you have to be able to generalize that to any group which it tells you is electron withdrawing. And then it says, well, okay, what's the consequence of that for the rate of an electrophilic substitution like nitration? And the key idea is, remember, that this is about attraction between the delocalized electron system, high electrons in the ring, and whatever your electrophile is. So in the case of nitration, remember it's NO2+. And basically, the stronger the attraction between the electrophile and the pi electrons of the ring, the more likely it is that a pair of electrons is going to jump out of the ring and be grabbed by the electrophile like that. So that's the key first step in electrophilic substitution. And how attractive that is just depends on the pi electron density. The more electron density, the more negative, so the stronger the attraction. That's what this is getting at. So what you explain is that decreased pi electron density in the ring makes it less attractive to an electrophile, like NO2+, but it just asks you in general here. So less attractive to an electrophile, and therefore less reactive than your reference compound, which is just benzene. Okay, so again, that story about the effects of electron withdrawing groups and electron donating groups, you've got to be confident about that. They could ask you about either one of them. But that's the story. You learn that for NO2 as a substituent, but you have to be able to generalize that to any group which it tells you is electron withdrawing. Now, the other thing you have to know about electron withdrawing and electron donating groups is their so-called directing effects. In other words, when you have one of these groups already bonded to a ring, you need to know that that affects where any subsequent substitution is likely to happen. So the story that you learn is that if you have electron donating groups, which would mean OH or NH2, for example, where you have a lone pair on the oxygen or nitrogen which can delocalize into the ring and boost the electron density, these direct to 2, 4 and 6. And you typically get multiple substitutions. Because these things have activated the ring, made it more reactive with its increased electron density, it tends to react multiple times. So, for example, if you have phenol with its electron donating group, it activates the ring at the 2 and 4 and 6 positions specifically. And because of the increased reactivity, if you add, for example, bromine, all 3 of those will react. And you get this outcome. Now, you don't have to explain why it goes to 2, 4, 6, because that requires a more sophisticated model of what's going on in the intermediate than we use at A-level. You just have to learn 2, 4 and 6. But that's not what this is about, because this was talking about an electron withdrawing group. So if you have an electron withdrawing group, the easy way to remember is that it goes to the other positions, which would be 3 or 5. So NO2, but in this case our electron withdrawing group is an acyl group with a C double bond O there, and this directs to 3 or 5. And I've written or rather than and there because of the lower reactivity resulting from the decreased pi electron density. Usually it will react only once. I mean, that's not a hard and fast rule. You can make it react more than once, but when it asks you for the product, if there's an electron withdrawing group there, you would normally just go for a single reaction at the 3 or 5 position. So in our case, you've got this compound, you've got this compound, and that's the 1 position. So the 3 position is this one. And so that's going to be the major product because of this being an electron withdrawing group. So again, just learn the directing effects. Don't worry about why that happens, because as I say, that's not something you need to know about, but you just need to learn that you would get made primarily the 3 substituent there, like that. The other question it had about nitration was just what's the suitable catalyst. So you have concentrated nitric acid. And again, as always with catalysts, all you can do is learn them. There is no way you're going to make those up. So in this case, the answer was concentrated sulfuric acid is the catalyst. So H2SO4 was the formula that you wanted. So then it asks you about isomerism. And the question was, what's the total number of stereoisomers of this compound that can exist? So you need to remember the story. Stereoisomerism, remember, means that you have more than one compound which has not only the same molecular formula, but the same structural formula, meaning the bonds are connected together in the same order, but a different arrangement in space. And what we've now learnt is that that comes in 2 varieties. There's EZ isomerism, which can be an issue when you have alkene groups, and there's optical isomerism, which is an issue when you have chiral centers. So when you get general questions about stereoisomers, you need to look for both of those things, EZ isomerism possibilities and chiral centers. So EZ, well, this is the alkene group, and the requirement for EZ, remember, is that you can only get EZ isomers if you have 2 different groups attached to each of the carbons of the double bond. So is that true? Well, here's the first one, and you can see it has a hydrogen, which we don't see in the skeletal formula, but you hopefully know that's there, and that's obviously different from this group. So yes, at this end we've got 2 different groups. What about here? Well, again, we've got a hydrogen down here and a methyl group. So we have got 2 different groups at each end, and therefore we have got EZ isomerism. So we've got 1 alkene group that does that. What about chiral centers? Remember, a chiral center is a carbon with 4 different groups around it. So anything that's unsaturated can't ever be a chiral center, because if it's got an electron involved in a pi bond, it can only have 3 sigma bonds, so it can't have 4 different groups around it. So we can immediately rule out that carbon and that carbon and that carbon and any of the ones in the ring. They can't ever be chiral because they're not bonded to 4 things, let alone 4 different things. So that actually only leaves 2 candidates, this carbon and this one. This one obviously isn't chiral because it's got 3 hydrogens bonded to it, which are all the same. But this one is, because you can see that that carbon has got 4 different groups. So this organic group is different from that one, is different from a methyl group, is different from a hydrogen. So 4 different groups there mean that that's a chiral center, and we have 1 chiral center. And so if we want to say how many stereoisomers can there be, then you can think, right, well, if we focus on the alkene group, it can be either E or Z. And the chiral centre is completely independent of that, so it doesn't matter whether it's E or Z. The chiral centre can either be right or left-handed. You don't have to know the proper naming system for optical isomers, so we can just think of them as the right and left-handed forms. So the same, that the Z can be right or left-handed. And therefore, you can have 4 possible isomers is the example. The general rule, which will usually give you the right answer, is that you can have 2 to the n stereoisomers, where n is the sum of the number of EZ type alkene groups and the number of chiral centres. So that's worth remembering. But usually they won't give you big numbers like that, but 2 to the n is the rule if you do get bigger numbers to work with.